Well, I'm going to move now to English because our next invited speaker is Jürgen Schiffele from the Institute of Material Science at FECYC, the National Research Council. Jürgen has a PhD in quantum optics by the Potsdam University in Germany. He moved to Spain a few years ago, and since then he has been working at the Universidad Complutense de Madrid and nowadays at the Institute for Material Science in Canto Blanco. His research is devoted to theoretical properties and the seek of new applications of graphene, and he's going to show us some results, future applications of graphene plasmonics.
I work at the ICMM in Canto Blanco now, in Paco Guinea's group, and I'm nowadays doing things on graphene optics, or let's say optics with two-dimensional materials. And, well, as Pedro said, as Jorge said, I'm a physicist, I'm a theorist, to make it even worse. And today I'm going to speak about plasmonics. And I put you these two pictures here. This, no, like this. This is the dispersion of a plasmon in graphene, and eventually I have to explain you what this actually means. And this is the sketch of some device which we made to excite these plasmons in graphene. And this is work I did with Jorge Pedros. It was actually his idea, and is so far a theoretical proposal. But okay, to get started, first of all, I should explain what plasmons are, then what they are good for, and then why, out of all possibilities, one would want to use graphene as a plasmonic material. Okay, so let's go. Plasmons. What are plasmons? Their full name is surface plasmon polaritons, as written here. I call them plasmons for brevity, and they are essentially light waves, let's say, which are trapped to the surface of some conducting material, because the light interacts with the electrons in there. And that's just what we see here. Now you have a piece of metal, you have electrons inside there, and now if these electrons oscillate collectively, they make a movement like this, no? Then outside of the material, of course, you see an electromagnetic field. This is just what happens when you move a charge. And good. Then this oscillation can propagate along the interface, for example, like a wave, no? The energy cannot get away from the interface. That's the trick. Because here in this direction, this electromagnetic field is evanescent. Pardon. No. Jesus Christ. Okay. Yeah. And why is all this useful? Now it turns out that the wavelength of this oscillation is much shorter than the wavelength of light at the same frequency. I'll show this here. See, if we have light of some kind of frequency, then it's the year of light. Light is on the light cone here. It has a wave vector like this, go down from this line. And the yellow curve here is the dispersion for a plasmon in a conventional metal. So you see, you come in with a frequency, and the dispersion of the plasmon is way to the right of the light cone. Means higher momenta, means shorter wavelength, and we are here. So visible light has a frequency of, let's say, order of magnitude a micron, no? Half a micron, okay? And we are at the micrometer scale. And at the same frequency, a plasmon is at the nanoscale. So we can just imagine plasmons as compressed light. Plasmonics is a means of making light small. And this is the most important feature of plasmonics, because this allows us to beat the diffraction limit, which limits classical optics, no? Because in classical optics, you can't make things smaller than half the wavelength. And in plasmonics, you can. For example, one hope is to make integrated photonic circuits. And, well, something like this. No, this is electronics. Here we see something which is commonly called a microchip, which is integrated electronic devices all on one platform. And the typical dimensions here are nanometers. And, oh no. And here you see an optical experiment. And good, I admit I choose a big one. But this thing here has mirrors and lenses. And you cannot make this smaller than half a micron if you work in the visible. Let's say that's the limiting scale. And now, obviously, you won't get this on a microchip. So one big hope of plasmonic research is that once upon a time we would be able to make plasmonic devices which could integrate like optical elements on a single chip and then build something like a computer which works not based on photonics, not based on electronics, but on photonics with light, no? Integrated optical circuits. And the obvious other possibility is if plasmonics makes light so very small that it's on the same length scale as electronics, then they can as well, both of them work together in the same machine. And this would also be very useful, actually. Why? What you see here is, well, from the 1970s. That's a sample of very conventional electronics. That's the Cray 1 computer. This is approximately as tall as me, slightly taller. And I show this why. Why do you think they made this in this hemispherical shape? They had to build it like this because if it would be just straight, then the cables here in between the components, which link different processors, let's say, would be too long. Like this, they can make all the connections shorter. And like this, they could get it to work that fast. And these things haven't changed that much since the 1970s. In multi-core machines and big computers nowadays, still one major limit for making the processing speed up for making the thing faster is the interconnects between the processor cores, the interconnects that bring digital data from here to there. And well, now you've got the obvious idea is, why don't you make a faster cable there? Make a fiber optic cable. This is what Telefonica is trying to sell you. They have more data capacity than just an electronic wire. So make an optical wire in between the cores. And now it won't work. Why? Optical cables are much too big for electronics. We've seen this. And so one promising idea, also just a proposal as far as I know, would be to interconnect different processor cores or different digital components with plasmonic structures like just little metallic strips or something, plasmonic wires, which could carry digital data in the form of plasmons. And these could be small enough to be integrated on a chip. And another idea, this here comes from the Basque, no, where are these guys from? Barcelona or are they from the Basque? Barcelona, no, yes. Yeah. The other idea would be to make it wireless altogether. And what you see here are different processor cores, no? And each of them has now a little plasmonic antenna. Each has its own antenna. And then they talk with each other just via their own Wi-Fi network. And this might also help to speed the computer of the future up. And I have one more application, and that's the only one to my knowledge which is so far commercially available of those I show. But this here already for sure works, but has nothing to do with graphene as I show it here. Plasmonic sensors. Now what we see here is a very small gold particle, a nanoparticle, a couple of microns long. And now it turns out if you shine light on this with the right kind of resonance frequency, then you can make the electrons in there going like whoosh, 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 like a standing wave, which is a plasmon oscillation. Yeah. And you see this in the absorption spectrum, of course. No? When the light excites this plasmon, then it's gone. So you get an absorption peak here, the blue curve. And now if another polarizable particle, one of these green molecules here, for example, comes near the gold particle, this changes the dielectric environment locally, no? There are different conditions for the electric field. And this in turn changes the frequency of this plasmon oscillation. And this you can see in the absorption spectrum. And then, well, you can see a shift in this peak. You read this out optically. And then this little gold nanoparticle can act as a sensor, which can can detect the presence of one of these single grain molecules, for example. And everything I told you so far is not connected to graphene, actually. Now, the big question, if you can do plasmonics with metals or with any conductor, why should you use graphene? Okay. Well, this is the slide for graphene. I don't have to tell you everything now. The picture from Wikipedia and how it looks in reality. Well, one thing which is connected to optics, it absorbs in the visible frequency range to let's say 2% of light, no? That's why we can see it. Here is nothing at all. Here is one layer, here is bilayer graphene, and you see it's slightly darker, and that's how they found it, actually. And, well, we have this peculiar linear band structure for the electrons, the Dirac electrons. And what are the practical consequences of this? We have high carrier mobilities. What is happening is that graphene is a metal, okay, but it's a pretty lousy one, actually, in terms of electron densities. There are only very few electrons in there. But what counts is the mobility, which is the conductivity per charge carrier, which is more or less the conductivity caused by one electron. This is a high number. This is comparable to good metals. If you get a good graphene sample, people can do this. And this is what we need for plasmonics. Why? Plasmonics wants to make electrons go like this, no? And if you want a charge oscillation like this, you don't want it to be damped out. And that's why you need mobilities. And that works. This is a recent article. That's from the ICFO now, from Coppens Group in Barcelona. And, well, they measured, let's say, typical decay times for plasmon oscillations in graphene. They can make very good samples. These are special samples. Okay, this is encapsulated graphene and boron nitride. But whatever, what they get is a number, 500 femtoseconds, and this doesn't tell much. But if you compare this to how long a plasmon lives in silver, for example, this is one order of magnitude smaller. So we get a factor of 10 here in the plasmon lifetime. Okay, this is one thing that graphene can do for us in plasmonics. And the other thing has to do with the very obvious fact that graphene is just atomically thin. What happens if you have a sheet of graphene, let's say, and apply an electrostatic field, a gate voltage? You can shift the Fermi energy, no? You can shift more or less the filling where the electrons sit in this dispersion here, from here to there. And very nice. But it turns out that this also gives you tunable plasmons. You can turn a knob in the laboratory and tune a plasmon dispersion. Goes like this, no? Well, okay. To calculate how the plasmon really looks like, we have to think about how two electrons in graphene interact with each other. And this happens as in any conductor. There are lots of electrons, and if one electron is here and the other one is here, then their interaction is screened by all the other ones in between. And the details of how this happens is usually described by some dielectric function. And let's suppose we calculate this, and we can. Then this is a function of wave vector, which I plot here, and of frequency, which I plot here. And when this thing here is 0, then the interaction between two electrons is strong. And this is where we get a plasmon, because then they will go together. Now I plot this, and, well, I get this red curve. What happens up here? We open a kind of decay channel at these energies. You can make interband transitions here, and then the plasmon decays. That's why the curve stops here. But okay, down here it's stable. And this dispersion just looks like this. Frequency of the plasmon goes like the square root of the wave vector, and that's not spectacular. But the spectacular thing is the Fermi energy is in here, And that's what I told you. You can tune this in the laboratory almost at will. So one unique feature in graphene is you can tune this plasmon dispersion up and down here. And if you have anything else, like a laser or a quantum emitter or whatever, you can get the plasmon in and out of resonance. And good. Now, I haven't told you yet how you actually get graphene plasmons. How do you excite them? I just told you it's an oscillation of charges, yes, but how do you make this? Shine light on it, approximately, yes. But it won't work so easy because the problem is, again, here you have the dispersion now of the graphene plasmon. And this diagonal line here in this plot, this is the band of the graphene electrons. That means the diagonal line here is k vector times Fermi velocity. And if you have an electron, if you have a photon, if you have light from a laser beam, these photons will be on the light cone. And the light cone is what? Is c, the vacuum light velocity, times wave vector. And in this plot, this is horizontal, because the velocity of light is 300 times steeper than this line here. Okay, so you want to excite the plasmon, you shine laser on graphene, then your laser has a frequency, that means on the frequency scale it comes in here, and on the momentum scale it sits here now, and then you have to go way to the right to the plasmon dispersion to conserve momentum. And how do you want to do that? Well, one trick to do that is to take your light and to scatter it on something, preferably something periodic, which has a sub-wavelength structure. You need something very small. And this is an image I stole from a textbook. This is what happens when you shine light on a grating of sub-wavelength dimension. And light comes in here, and most of it goes through, of course, in zeros order, and then you have diffraction order 1, 2, 3, -1. And what happens here is, well, the wave vector of the light picks up some momentum, otherwise it wouldn't be to the right, which is somehow proportional to this lattice spacing. And this is the mechanism that people use to get my photons from the light cone, from here to there to the plasmon dispersion, and then they can excite plasmons in graphene or in anything else. And so, important message. The only important thing about this formula, if you want to launch plasmons, you need something small where you shine your light on. And then various people have tried these in the last 5 years with graphene. Actually, not before. It's a pretty young branch of, let's say, physics. And the first thing here was this here. This is well, good, 2 groups, let's say. But what they do is they take light here. Here is graphene, and they shine it on the tip of an atomic force microscope, an AFM microscope. And this tip is metallic and very sharp. And the light has a wavelength of 10 microns, let's say. That's in the terahertz somewhere. And the tip is much smaller than this. So if you shine light on it, it reflects light. And then because of the spatial concentration, this light, which comes back from the tip, has a large momentum uncertainty. And like this, it can get on the plasmon dispersion and excite these circular plasmon waves here. And what happens then, what they actually saw, is that these plasmon waves travel out to the edge of the graphene flake, travel back, make an interference pattern. And they took the same atomic force microscope to measure that interference pattern, because then you can, of course, look how the field looks like. And like this, they measured the plasmon wavelength, things we see here. These are standing electron oscillations. Here you fit 2, here you fit 1. And they found that these plasmons here have a wavelength 40 times shorter than the wavelength of light, which they put in. So they managed to compress light by a factor of 40. And okay, they also varied the Fermi energy, and everything works as expected. And these were the proof of principle experiments 3 years ago. But this is not practical, because if you want to build a device, you don't want an atomic force microscope to carry around. So what other people did more recently, this is again people from the ICFO mainly. they, instead of the AFM tip, they take a little gold particle here, 3 microns, which acts like an antenna. They put this directly on the graphene. Then they shine light on this thing. And well, then this antenna radiates in the near field, and this near field radiation is exciting plasmons in the graphene here. And another approach, much more simple, actually, is not to put anything there, but simply to cut the graphene itself. Remember, we need small structures. Well, then let's make the graphene small. This is from the IBM group. What you see here are graphene ribbons. This is graphene substrate, and these ribbons here are, well, a few nanometers, 100 nanometers, let's say. And then what happens again, if you shine light with polarization like this, then you excite in this ribbon a standing electron wave, and that's your plasmon. And that's from the IBM group in New York. And the problem with that is just that if you have to cut graphene, then the edges are usually not very clean. They are passivated or whatever, and if the electrons scatter there on this dirt, this has rather negative effects on the plasmon lifetime. So this is not for making long-lived plasmons. And this is where the idea of Jorge comes in, because Jorge told me that, well, we could as well make this structure in graphene without cutting it. And we came up with something like this. In the end, the idea was to take graphene and put it on a substrate, which is piezoelectric. And a piezoelectric material has the feature that if you somehow attach electrodes to it and apply a voltage, you can make it move, deform. Yeah, that's what a piezoelectric does. So we apply an AC voltage here, which makes the whole thing vibrate. And more precisely, we launch a surface acoustic wave, which is this deformation you see at the top. This deforms the graphene. And then we make something like this, yes, electrically out of the graphene. And then we have our sub-wavelength structure, shine light on it, and can hopefully excite plasmons here, because this is the diffraction grating. And we don't get all the trouble with cutting graphene into ribbons, and we can switch the grating on and off electrically. The disadvantage, this is just a theoretical proposal so far, but hopefully we get this built soon. And good. So this is almost all I have to say. I hope what I showed you are a few facts, namely plasmons are compressed light, and this is very useful because you can make small optics, you can make integrated optics, you might eventually end up with a photonic computer instead of an electronic one, which would be much faster. And it is certainly a good idea to use graphene for plasmonics. The biggest advantage of graphene is the tunability of the plasmon dispersion, simply by applying a gate voltage. There are other possibilities. You can put graphene on a different substrate material, then you also get a different plasmon dispersion. I haven't even talked about that. And, well, the high carrier mobilities, which give long-lived plasmons. And, well, we heard a lot about these curves of technology today. I would say if the curve is like this, the first experiments on graphene plasmonics were just 2, 3, 4 years ago. We are somewhere here before it goes up. The applications come, many of the applications will come later, but it is in the agenda of the graphene flagship, an important point. The graphene flagship is actually the thing that pays me. Thanks very much. And we are sure that there are many potential applications for graphene plasmonics in integrated photonic circuits, also in medicine, chemistry, biology, all the sensor stuff, and for electronic interconnects, for example, to speed up your iPhone number 8 or whatever. Good, and with this I'm finished, and thanks.
So my question is, up to what extent affects things such as the geometry of the graphene sheet, such as defects, such as, I don't know, even the number of layers. I assume this only works in monolayer graphene, because if it is a resonance effect, it should be highly dependent on all these things. Is it?
It is, unfortunately it is. Device quality is critical. And there are plasmons in bilayer graphene too, but they look differently, the dispersion. So you won't get anything useful if you have a sample which is somewhere monolayer and somewhere bilayer. And if you want to make a good plasmonic device, you need really clean let's say you need really clean sample. And the best things that are available right now, or that have been done right now, are these well, I just, that's the citation here, no? These guys are from the ICFO, Frank Coppens, and is the group leader, and what they did, they used graphene which is encapsulated by boron nitride, like a sandwich. And now it seems like when the graphene, the monolayer graphene, is in between two boron nitride layers, then it's like ironing a shirt, let's say. All the wrinkles are smoothed out, and then they get these super high mobility samples. And the technique by which they make them is they call it, actually I'm not very firm with that, the polymer-free van der Waals deposition. They somehow stack these things together, and I'm afraid this is not scalable right now on an industrial scale. But probably, hopefully, these things will be solved in the future. In the laboratory, it works. For industry, this technique is probably yet too expensive. But in principle, if you have a clean sample, graphene plasmonics will beat conventional plasmonics and conventional optics.
And what about the substrate? I mean, can you use any substrate? Do you need a specific substrate to work?
You can use any substrate, but the result will depend on the substrate. Let's put it like this. Especially what people have. Maybe I have a few slides here. Huh? Yeah. What you see here is the dispersion of a graphene plasmon when graphene is on silicon dioxide, yes. And then the point is silicon dioxide has optical phonons. They are excited, I mean, they are polar phonons, and they have frequencies here and here. And this is like how the graphene plasmon should look like on a completely inert material, no? And it doesn't. It hybridizes here, because here the graphene plasmon excites a phonon in the substrate, and here the graphene plasmon excites a phonon in the substrate. And what you get are coupled oscillations of phonons and electrons all together. And this is not necessarily a bad thing. Actually, they are very long-lived, because a phonon has a longer lifetime normally than an electron vibration, because, well, the ions are heavier, kind of. But what you get depends very strongly on the substrate, and this is actually more a feature than a bug, because you can engineer many things with that.
Okay. Thank you.
Some other questions? Okay, now let's thank the speaker again.